What is a full adder? How carry-in makes binary addition work. In the previous lesson, we learned how a half adder can add two binary bits. A half adder has two inputs, A and B, and two outputs, sum and carry. An XOR gate produces the sum, and an AND gate produces the carry. That works perfectly when we only need to add 2 bits. But computers usually work with much larger binary numbers, 8-bit, 16-bit, 32-bit, or 64-bit. When several bit positions are involved, a new problem appears. A bit position may receive a carry from the previous position. A half adder cannot accept that incoming carry. To solve this problem, we need a full adder. A full adder adds 3 1-bit inputs and produces a sum and a carryout. Chapter 1. The problem with the half adder. Consider the binary addition 11 plus 0 1. Start with the rightmost column. 1 plus 1 equals binary 1 0. We write 0 as the sum and carry 1 into the next column. Now the next calculation is not simply 1 plus 0. It is 1 plus 0 plus 1. That third bit is the carry from the previous column. But a half adder has only 2 inputs, A and B. It has no place for that incoming carry. This is exactly the problem the full adder solves. Chapter 2. 3 inputs, 2 outputs. A full adder has 3 inputs, A, B, and Cin. Cin means carry in. It produces 2 outputs, S for sum and Cout for carryout. So the full adder calculates A plus B plus Cin. Because each input is only 1 bit, the largest possible calculation is 1 plus 1 plus 1. That equals 3, or binary 1 1. So 2 output bits are enough. For 1 plus 1 plus 1, the sum is 1 and the carryout is also 1. Chapter 3. The full adder truth table. A full adder has 3 binary inputs. Each input can be 0 or 1. So there are 8 possible input combinations. For 0, 0, 0, the result is sum 0, carryout 0. For 0, 0, 1, the result is sum 1, carryout 0. For 0, 1, 0, the result is sum 1, carryout 0. For 0, 1, 1, the result is sum 0, carryout 1. For 1, 0, 0, the result is sum 1, carryout 0. For 1, 0, 1, the result is sum 0, carryout 1. For 1, 1, 0, the result is sum 0, carryout 1. And for 1, 1, 1, the result is sum 1, carryout 1. These 8 cases completely describe the behavior of a full adder. Chapter 4. Finding the sum. Now look only at the sum output. The sum becomes 1 whenever an odd number of the 3 inputs are 1. This is exactly what XOR does. So the sum equation is S equals XOR B XOR Cin. We can calculate it in 2 steps. First, X equals XOR B. Then, S equals X XOR Cin. This gives us an important clue about how the full adder circuit can be built. Chapter 5. Finding the carryout. Now look at the carryout. Carryout becomes 1 whenever at least 2 of the 3 inputs are 1. For example, 0 plus 1 plus 1 equals binary 1 0. So the sum is 0 and carryout is 1. The same happens with 1 plus 1 plus 0. And 1 plus 1 plus 1 produces binary 1 1, so it also has a carryout of 1. One useful expression is Cout equals A and B, or Cin and XOR B. This form is especially useful because it shows how a full adder can be built from half adders. Chapter 6. Building a full adder from 2 half adders. A full adder does not need to be designed from scratch. We can build one using 2 half adders and 1 OR gate. The first half adder adds A and B. Its sum is X equals XOR B. And its carry is C1 equals A and B. But the calculation is not finished yet. We still need to add Cin. Chapter 7. The second half adder. The second half adder takes X and Cin as its 2 inputs. Remember that X equals XOR B. The second half adder calculates X plus Cin. Its sum is S equals X XOR Cin. So, S equals XOR B XOR Cin. The second half adder can also produce another carry. We call it C2. C2 equals X and Cin. Now we have the final sum, but we still need to determine the final carryout. Chapter 8. Why do we need the OR gate? There are now two possible carry signals. The first is C1, produced when A and B are both 1. The second is C2, produced by the second half adder. If either carry is 1, the full adder must produce a carryout. So we combine them with an OR gate. Cout equals C1 or C2. In this straightforward design, the complete full adder uses 2 XOR gates, 2 AND gates, and 1 OR gate. That is simply 2 half adders connected together, followed by an OR gate. Chapter 9. Walking through an example. Suppose A equals 1, B equals 0, and Cin equals 1. We want to calculate 1 plus 0 plus 1. The answer should be binary 1, 0. First, the first half adder calculates a XOR B. 1 XOR 0 equals 1. So x equals 1. Its carry is 1 and 0, which equals 0. So C1 equals 0. Now the second half adder adds x and Cin. 1 plus 1 equals binary 1, 0. The sum is 1 XOR 1, which equals 0. And C2 is 1 and 1, which equals 1. Finally, the OR gate combines C1 and C2. 0 or 1 equals 1. So carryout is 1, and sum is 0. The final result is binary 1, 0. Exactly what we expected. Chapter 10. Half adder versus full adder. The difference between a half adder and a full adder is simple. A half adder has two inputs, A and B. It calculates a plus B. A full adder has three inputs, A, B, and Cin. It calculates a plus B plus Cin. So the most important difference is not simply that the full adder has more gates. The important difference is that it can accept a carry from the previous bit position. That is what makes the full adder useful for multi-bit arithmetic. Chapter 11. From one full adder to multi-bit addition. Now suppose we want to add two 4-bit binary numbers. We can use one full adder for each bit position. The first full adder adds the least significant bits. Its carryout becomes the carry-in of the next full adder. That carryout then moves into the next stage. The same process continues through all 4-bit positions. So each stage produces one sum bit and passes its carry to the next stage. By connecting several 1-bit full adders together, we can add complete multi-bit binary numbers. This is where a small logic circuit begins to look much more like the arithmetic hardware inside a processor. Chapter 12. Why the full adder matters. A full adder is a very small circuit, but the idea behind it is fundamental. It solves one of the key problems in binary arithmetic: how to pass a carry from one bit position to the next. A single full adder handles one bit. Several full adders can handle many bits. So the path is logic gates, then half adders, then full adders, then multi-bit adders, and finally computer arithmetic. We started with simple Boolean operations. Now those same operations are working together to perform arithmetic on complete binary numbers. Conclusion. A full adder is a digital circuit that adds three 1-bit inputs, A, B, and Cin. It produces two outputs, sum and carryout. The sum is S equals a XOR B XOR Cin. The carryout can be expressed as A and B, or Cin and a XOR B. A straightforward full adder can be built from two half adders and one OR gate. The first half adder adds A and B. The second half adder adds Cin. And the OR gate combines the two possible carry signals. The most important improvement over the half adder is carry-in. Because one full adder can receive the carryout from another full adder, these circuits can be connected together to add multi-bit binary numbers. And that leads directly to the next question: what happens when we connect several full adders together? The answer is the ripple carry adder.